Alright, let's pick back up and finish up the lecture for Chapter 3. We had gotten to data dictionaries. Data dictionary provides a detailed description of all tables in the database created by the user and designer. The data dictionary contains at least all the attribute names and characteristics for each table in the system. In short, the data dictionary contains metadata, or data about the data. Alright, the system catalog can be described as a detailed system data dictionary that describes all objects within the database, including data about table names, the table's creator and creation date, the number of columns in each table, the data type corresponding to each column, index file names, index creators, authorized users, and access privileges. Because the system catalog contains all required data dictionary information, the terms system catalog and data dictionary are often used interchangeably. In fact, current relational database software generally provides only a system catalog, from which the designer's data dictionary information may be derived. As new tables are added to a database, that documentation always allows the RDBMS to check for and eliminate homonyms and synonyms. Okay. In general terms, homonyms are similar sounding words with different meanings, such as bore, B-O-A-R, and bore, B-O-R-E. Or a word with different meanings, such as fair, which means just in some contexts, and festival in others. In a database context, the word homonym indicates the use of the same name to label different attributes. For example, you might use C_name to label a customer name attribute in a customer table, and use C_name to label a consultant name attribute in a consultant table. To lessen confusion, you should avoid database homonyms. The data dictionary is very useful in this regard. In a database context, a synonym is the opposite of homonym and indicates the use of different names to describe the same attribute. For example, car and auto refer to the same object. Synonyms must be avoided whenever possible. Okay, it talks again about relationships within a relational database. You have one-to-one, one-to-many, and many-to-many relationships. The one-to-many relationship is the relational modeling ideal. Therefore, this relationship type should be the norm in any relational database design. One-to-one should be rare in any relational database. And many-to-many relationships cannot be implemented as such in the relational model. Later in this section, you will see how many-to-many relationships can be changed into one-to-many. And then a composite entity, bridge, or associative entity helps avoid problems inherent to many-to-many relationships. It includes the primary keys of tables to be linked. Okay. And then here we show a one-to-one relationship between professor and department. And here we show the changing the many-to-many relationship into a one-to-many. And then the expanded ER model. Okay. Let's talk a little bit about data redundancy. Relational database facilitates control of data redundancies through use of foreign keys to be controlled except the following circumstances. Data redundancy must be increased to make the database serve crucial information purposes and exist to preserve the historical accuracy of the database. Okay. Now let's talk about this relational diagram for an invoicing system. You have your customer, and you have your customer code, which is the primary key, which is the foreign key in invoice. So your invoice number is the primary key in invoice, and customer code links back to customer for your – invoices. And then your line number and invoice number combine to create the primary key, and the invoice number is also the primary key in invoice. So it means that it won't be unique with within line. It can be duplicated, but with the line number it creates a unique identifier for line. And then your product code is your primary key in your product table, but it is your foreign key in your line table. Okay. Alright, so let's go back and look at this. Does this create data redundancy? Yes and no. You have your customer code listed in two places and your product code listed in two places because it's the primary key in one table and it's the foreign key in another table. So yes, you do have some data redundancy, but it is to create the relationships between the tables. Alright. Orderly arrangement to logically access rows in a table is created with an index. Your index key, in effect, is the index's reference point that leads to the data location identified by the key. The unique index is index key can have only one pointer value associated with it, and each index is associated with only one table. Okay, so they didn't demonstrate this. Okay, if you look on page 101, and it shows the components of an index, and as you examine this, note that the first painter number, or painter num, index key value is 123, and is found in records 1, 2, and 4 of the painting table. The second painter num index key value is 126, and is found in records 3 and 5 of the painting table. Okay? DBMSs use indexes for many different purposes. You just learned that an index can be used to retrieve data more efficiently, but indexes can also be used by DBMS to retrieve data ordered by a specific attribute or attributes. For example, creating an index on a customer's last name will allow you to retrieve the customer data alphabetically by the customer's last name. Okay, so that's a reason that you would use an index. So if you use this index, it will point more quickly to the correct painting title, because you would use the painter number and the record number to more quickly point out the paintings that were done by that particular painter. And then in table 3.8 on page 103, there's some relational database rules that you guys might want to go look at. All information in a relational database must be logically represented as column values in rows within tables. Guaranteed access. Every value in a table is guaranteed to be accessible through a combination of table name, primary key, and column name. Systematic treatment of nulls. Nulls must be represented and treated in a systematic way, independent of the data type. Dynamic online catalog based on the relational model is the metadata must be stored and managed as ordinary data. That is, in tables within the database, such data must be available to authorized users using the standard database relational language. Comprehensive data sublanguage. The relational database may support many languages, however, it must support one well-defined declarative language as well as data definition. view definition, data manipulation, integrity constraints, authorization, and transaction management. View updating. Any view that is theoretically updatable must be updatable through the system. High-level insert, update, and delete. The database must support set-level inserts, updates, and deletes. Physical data independence. Application programs and ad hoc facilities are logically unaffected when physical access methods or storage structures are changed. Local data independence. Application programs and ad hoc facilities are logically unaffected when changes are made to the table structure that preserves the original table values. Integrity independence. All relational integrity constraints must be definable in the relational language and stored in the system catalog. Distribution independence. The end users and application programs are unaware of and unaffected by the data location. Non-subversion. If the system supports low-level access to the data, users must not be allowed to bypass the integrity rules of the database. And Rule 0. All preceding rules are based on the notation that to be considered relational, a database must use its relational facilities exclusively for management. Alright, that concludes the lecture for Chapter 3. If you guys have any questions, let me know.